So Grab processes millions of foods and mart orders every single day, and the most critical but brittle part of the infrastructure is the database. Given how critical orders are to Grab, they have to ensure a very high availability of the database while ensuring a very fast query time. So how do they achieve this? In this video, we take a look at a very high level architecture of the data layer of Grab's order platform and see the practices they follow to ensure high availability, stability, and performance at scale. So the first step towards architecting a database layer for any such product, any such service, any such system like this is to understand the kind of queries that we would fire onto this database, right? So there are two kinds of queries that we typically fire. First is transactional queries, second are analytical queries. Now transactional queries are classically basically getting something, updating something, deleting something, right? So basically get an order, create an order, delete an order, update an order. These are transactional queries. Second are the analytical queries where you might want to get historical orders of a particular user or some statistic around orders. Let's say grouping orders by a particular attribute, right? These are analytical queries which can take some time and it's okay, right? So we would be leveraging that. Now, with respect to Grab, one very interesting thing that happens is they have to be very good at handling spikes because the traffic for a platform like Grab would not be uniform. It would be spiky in nature because let's say there is a dinner time, you would see a huge surge, and specifically around a particular time window, you would see a massive influx of surges. Or maybe there is an event and a lot of people order from food and mart on Grab, right? So which means that handling spikes is really important, right? So then let's talk about design goals. Now this entire thing is taken from Grab's engineering blog, which I've linked in the description down below. I would highly recommend you to check that out. So with respect to Grab, their design goals were pretty simple and straightforward, but really important. First one, stability. Now, when you are architecting a database layer, given how critical database is to any system, because if database is down, everything is down. So given how critical database is, the most important part or the most important criteria for a good design has to be stability. That the system has to be stable enough, which means it needs to handle a very high level of query per second that would come in. Plus it needs to be available because given the database is the one that is storing the order, basically creating and getting the order, which means that if this database goes down, it is loss of revenue, which means that your data layer has to be highly available. Then with respect to availability, you can also sense that, hey, in case there are failures, because failures are inevitable, in case there are some failures here or there, it can have degraded performance impact on your system, but it should not lead to a complete outage. So it's okay for some fragment to be down, but some fragment down should not lead to a complete outage. This is really important for your business to survive. Second design goal is around being cost effective. It's really important when a company operates at scale, a small slow query or a simple looking slow query would shoot your infrastructure cost by a huge margin when you talk in absolute terms, which means your architecture has to be very cost effective. Third, consistency. This is so important. Like you would not, as a user, when you're using Grab, when you create an order, when you go to the page to see your historical orders, you don't want, arey, my order is not there. You want strong consistency for transactional, but eventual, still fast enough, but eventual consistency for analytics load. So because transactional queries are really important, because when you are updating an order, it needs to update right there and then. You cannot just say, I will update it with some delay. So you need strong consistency for transactional queries and eventual consistency for analytics queries. Now these are design goals. Now let's see how they architected the data layer considering these things. Now first step is, because there are two types of queries, one transactional, one analytical, what if we create or we use two types of database, one specializing for transactional side, one specializing for analytics side. Now here a key point to note that these analytics is not gigantic analytics. You may not need a data warehouse per se, but a query that is good with analytics kind of stuff, right? We'll take a look on the kind of tech that they choose. So transactional database, they are called OLTP, online transactional processing database, and analytical database, because this is online, which means you need almost right there when you fire the query, you need immediate response. You don't want delayed response. So these are OLAP database, which is online analytical processing database. So first, let's take a look at OLTP database. So OLTP databases are databases which are meant for transactional purposes, which means that they would be the single source of truth no matter what, right? Because that is where your orders would be created, updated, deleted, and whatnot, right? Now, these databases are meant to be transactional in nature, which means that any interaction coming from the user will be directly going to this database. There would not be any asynchronous processing over here. So which means they need to be able to sustain a huge amount of load. So these databases are specialized to be transactional in nature, right? And they may not hold all data because it's okay if your historical data is moved to some other place, right? So these are key design decisions, right? We would be taking into consideration when we are architecting it. Then OLAP database. Now OLAP database would have same data as transactional database, but even larger, because we may delete data from transactional, but not delete from OLTP. OLAP. OLAP would have all data. We would use it for statistical processing. The data would be stored for a very long duration. Let's say 3 years old orders will also be there. And these database would be designed, or the database that we choose over here would be specialized to make analytics efficient, right? So different databases for different use cases. Then obviously the next problem that comes in, that how do we keep these data in sync? A classic way is to build a data ingestion pipeline, whose job is from your order service, whenever you need any transactional thing, you go to a transactional DB. Let's say you use DynamoDB or you may use DynamoDB for this purpose, or people use relational databases as well, like like MySQL, Postgres and all, or MongoDB. Whatever floats your boat, any transactional database would work. So long as it provides you strong consistency, right? But given that you need to have, now you're having two databases, one transactional, one analytics, you need to keep these two in sync. Classic way, when your transactional thing is done, you push a message to Kafka, consumed by workers, eventually being updated, like eventually being persisted in your analytics database. Redshift, BigQuery, or you may use any other. We're still not converged what to use. We will see what we can use over there. But this is a standard way to do it, right? So transactional goes to your transactional DB. Analytics asynchronously goes to your analytics database, right? Okay. Third point. Now, how do we choose a database? So let's say we have to make a choice for what type, like we want to choose a transactional DB. In order to choose a transactional DB, we need to understand the kind of queries we would be firing on that and see how it fits the need. So here with respect to Grab, what happened is, given the transactional database was going to use for get an order, delete an order, update an order, create an order, it's a key value use case. So what they went for is they went for DynamoDB, because DynamoDB number one is managed. So you get scale and it being highly available out of the box, because it's AWS's headache on how to do it. We don't have to worry, because at the end business matters, not how much are you managing your own infrastructure, right? So DynamoDB is scalable, highly available, brilliant. So we offload that part, and given our use case or Grab's use case is pretty straightforward, we can very well afford to do this. Second, DynamoDB, because we want strong consistency from our primary database, DynamoDB provides strong consistency for primary key reads, right? So for a particular key, which is the primary key of the table, you fire the query get, put, create, delete, it would give you consistent view of it. You need it. So DynamoDB fits that criteria. Third is really interesting. So here what happens is, this is beautiful part of DynamoDB. If you have not read DynamoDB's paper, I highly recommend you to do that. But in general, DynamoDB is known to handle spikes, and which is what Grab also needed. So, but how do DynamoDB do that? So what DynamoDB does behind the scenes is that it sees, because internally DynamoDB stores data in multiple partitions, right? So the data is partitioned inside DynamoDB. So when that is the case, when it gets the load, it on the runtime, it decides where to forward the request to, depending on the partition. But if a particular partition is hot, because let's say a few keys are constantly getting requests and that partition becomes hot, what DynamoDB does, it literally moves the data into some other partition, not hot, but the data which is infrequently accessed, it moves to a shared partition, while hot partition gets its own set of full capacity of the underlying infrastructure. This way, DynamoDB internally does that. We don't have to do anything there. DynamoDB internally handles hotkey problem seamlessly. right? And this is brilliant part of DynamoDB, which is why Grab went for DynamoDB. And again, all of this is taken from Grab's engineering blog, linked in the description down below. Highly recommended to check that out. Now, apart from just using DynamoDB, it also matters how smartly do you use it, right? So here there is one brilliant insight which I personally loved when I was going through the blog. So let's take a look at their schema. So given that all we want to store is orders, we would have orders table in which we have order ID, the state of the order, which means is it ongoing or completed or cancelled, something around that. Created it means at this time the order was created. User ID, I mean who placed the order. And there is one more key called user ID GSI. So So orders table has orders ID as the primary key because you want to get an order, delete an order, basically put an order and whatnot, right? So that is a primary key. But you would also want to fetch the ongoing order of a particular user, won't you? You need that. So given that, you would need an index on user. So you create a global secondary index on user. So you do that. But now what happens is this global secondary index is managed by DynamoDB. We don't have to do anything. We just create an index and it powers that. But now this index, the common query that we are firing on this database would be give me ongoing orders of a particular user, right? Once the order is moved from ongoing to completed, we would not be querying on this DB because we have another database to do it. So because we are never going to query on that particular attribute, when an order goes from ongoing to completed, we would never query that, which means that we can remove it from the index. But how can we directly remove from the index? This is the brilliant part over here. So what they do is so they created this key user ID underscore GSI. They didn't create an index on user ID. They added a new attribute called user underscore ID underscore GSI and they created a global secondary index on this attribute, right? Okay. So now what they do, when an order is created and it goes into an ongoing state, by default, the first state is ongoing state. It sets user underscore ID underscore GSI is equal to user ID, right? Then when the order is moved from ongoing to done, they set this column, this attribute to null. User ID is still there, but user ID underscore GSI, this is set to null. As soon as this is set to null, the entry is removed from the global secondary index because this is null. That index does not hold anything. So the global secondary index would at a given point in time would only hold the entries that are of ongoing orders. This way, the index is very small. Such a brilliant optimization. I loved it when I found it. I like, God, this is interesting, right? So just to reiterate, orders table has order ID state created at user ID. Other meta fields would be there. We don't care about them. So partition key, the entire table is partitioned by order ID. Instead of creating a global secondary index on user ID in order to get ongoing orders of a particular user, they created another field called user ID GSI. It's a special field and they created global secondary index on this. When an order is created, user underscore ID underscore GSI is set to user ID, right? So that you can find ongoing orders of a particular user. But as soon as you move your order from ongoing to done, then you set this user ID underscore GSI to null, which would make it delete from the global secondary index. The entry would still be there in the orders table, but it would not be there in the index. It is basically implementation of partial indexing in DynamoDB. This way you keep the GSI, the global secondary index size very small. It would be equal to the amount of ongoing orders at any given moment, which means it would be very lean, which means when you fire the query to get the ongoing orders of a particular user, it would be lightning fast. Brilliant optimization. Right? Which is how you need to know database internals to leverage it to the full extent. Right? Okay, so they do this. And obviously, given that there is an analytics database in which the same data is already flowing through events, you will have TTL set on these rows so that, let's say you would want to keep only 3 months worth of data in this transactional DB while historical data goes to analytics DB. So you typically set TTL to 3 months. As 3 months pass for a particular key, the key would be automatically deleted by the DynamoDB engine. You don't have to worry about it, right? Okay. Fourth, which database would you pick for OLAP? Now, this analytics, this use case is analytics, right? So you may choose, hey, let me go for data warehouse. You don't need data warehouse. You still want to fire good chunk of queries. But why would you want to overkill with an analytics database? Because it's all about only orders. It's not humongous data that you need a data warehouse per se. You still want to support analytics. You still want to support statistics. You still want to power basic analytics on this database. But data warehouse would be an overkill, right? Because these are almost near real-time queries that you would want to support. So what Grab did is Grab chose MySQL as their analytics database, right? And the way they structured this information is such that they minimize the cross-shard query that needs to happen on MySQL. Now, this is the overall architecture that is there for their entire data layer. It's very simple, but few very interesting caveats over here. So, you have order service. You use DynamoDB as your transactional database. It offers you strong consistency that you need. Then, all the events from order service, they are sent to Kafka, right? Kafka gives you an SLA of 99.95, which means there is still chance of Kafka going down. So now what happens when Kafka goes down? You still have to handle that because high availability, you won't say that, hey, if Kafka is down, I won't push the data over here, right? No matter what your business should run. So, but first let's complete the happy part, then we'll check for the edge cases. So once the events are pushed to Kafka, a bunch of consumers read them and they update it in MySQL. Right? So consumers consume and ingest the data in MySQL. All the events flow near real-time eventual consistency. The data flows into MySQL. Right? Okay. But now, given the Kafka has an SLA of 99.95, there is still chance of this going down. So what do? What if Kafka is down? That is where, because Grab is on AWS, they have SQS as a backup option. So if Kafka is down, the order service pushes the same message to SQS. And which is then consumed by few consumers here and there and put into MySQL. So even if Kafka is down, you have a fallback. Now what if SQS is down? If SQS is down, AWS offers you a DLQ, which is a dead letter queue. So you configure SQS with the DLQ configuration and put it and have the consumer. So no matter what, your system, even if your Kafka is down, your SQS would do. If SQS is down, DLQ would work. That's AWS's guarantee. And which means that no matter what, your analytics database is getting the data eventually, right? But the lag is bare minimum, right? Okay. Few more edge cases. So when you are inserting the data in MySQL, you always have to do upserts, right? Now, why am I talking about upserts? Because what if given messages may come out of order? You never know. Messages may be processed out of order. So what do? What if an update event on an order comes before create event? You cannot just say, hey, my data is not there, so I'll drop that event, right? So that is where you do upserts every time that you are getting it. This way, even if you get out of order events, it would not matter, right? But now, what if you get two updates, such that the update 2 comes before update 1? So in that case, you cannot just apply updates every time, because then you would be overriding the later update with the previous update. Wrong, right? So that is where you will have a check with timestamp field that, hey, if I will update only when the update is newer one. Otherwise, I won't do that, because here you have to be very of the fact that messages may come out of order. So that is why two very important design decisions is we always do upsert in the database in order to handle update coming before create. And while we are updating, we always need to check for the timestamp that no matter what, we were never applying a past update on a later version of the data. Very important when you think about implementation. And yeah, this is how Grab handles millions of orders every single day around food and mart categories that they have. Such a brilliant architecture. The two micro nuances were such brilliant optimizations, where one with the partial indexing on DynamoDB, a lot, even I would have done created a global secondary index on user ID, but this is such a brilliant optimization where they added a new attribute and they created a GSI on that. Brilliant optimization. I hope you also found it as amusing as I did. And second one is how they ensured that, hey, your Kafka is down. They added it with SQS with the DLQ configuration and doing upserts, right? Instead of doing raw inserts over there, right? Very interesting data architecture that we see over here from Grab. And yeah, that is it. This is how Grab does it. I hope you found it interesting. Hope you found it amusing. This entire piece is taken from Grab's engineering blog, which I've linked in the description down below. Highly recommend you to check that out. And yeah, that is it for this one. I'll see you in the next one. Thanks a ton.